Hi everyone. In the previous video, we discussed about the epsilon delta definition of limit. Today, using that definition, we will be proving one of the most important theorems of limit called the uniqueness of limit. The statement of this theorem is that suppose some interval I is subset of real number r and c is limit point of I. If a function f from I to r has a limit, then that limit is unique. This means that limit f of x equals to L as x tends to c, then that L must be unique. By unique, it means that L must be one and only limit of function f. Function f cannot have more than one limit. Okay, let's prove this. Suppose limit f of x equals to L. Then according to our definition, we can write for every epsilon greater than 0, there exists some delta 1 greater than 0 such that the modulus x minus c less than delta 1 implies f of x minus L modulus less than epsilon by 2. And we have to show that the limit L is unique. We will approach this proof by indirect method. That means first we start by supposing that the limit L is not unique. That means function f has two limits L and L prime. Let's suppose if possible that f of x has two limits L and L prime. Therefore, we can write there exists delta 2 greater than 0 such that the modulus x minus c less than delta 2 implies f of x minus L modulus less than epsilon by 2. And suppose that these two inequalities by 1 and 2. What we are doing here is that as x is approaching c, the function f of x is approaching both L and L prime. So we start by supposing that there exists two limit L and L prime and the function is approaching both of them as x is approaching c. Now our ultimate goal is to show that as x is approaching c, we have to show that L will be equal to L prime. This is our ultimate goal. If we are successfully able to show this, then our theorem will be proved. This means L minus L prime, the difference between them must be 0. So if we are able to show this, then our theorem will be proved. So we are going to conclude this later. Okay, now our next step is to choose delta equal to minimum of delta 1 and delta 2. If we do this, then this delta will be true for both the inequalities 1 and 2. This delta 1 and delta 2 both are arbitrarily small number. We must suppose them as small as possible. So if we set delta to be the minimum value between delta 1 and delta 2, then this delta will work for both the inequalities 1 and 2. This means we can replace delta 1 and delta 2 from 1 and 2 and write it as delta. Therefore, 1 and 2 are true for delta greater than 0. Now, let's find the value of modulus L minus L prime, because we have to show the difference between them to be 0. If we are able to show that, then our theorem will be proved. Now, the difference between L and L prime, we can write this as L minus f of x plus f of x minus L prime whole modulus. They both are same thing. We have subtracted and added f of x. Now using triangle inequality, we can write this less than or equal to L minus f of x modulus plus f of x minus L prime modulus. Because a plus b whole modulus is less than or equal to a modulus plus B modulus. This is the triangle inequality, and we have used that here. Okay, now using the inequalities 1 and 2, you can write this as less than epsilon by 2 plus epsilon by 2. L minus f of x is less than epsilon by 2, and f of x minus L prime is less than epsilon by 2. You can see that in 1 and 2 here and here. So this means that is L minus L prime modulus is less than epsilon. So this was the reason I used epsilon by 2 earlier, because I knew that I will be adding both of them later on, and just to obtain epsilon and make it look good, I used epsilon by 2. This epsilon is arbitrarily small number, and you can choose it to be anything. So there is no any rule to choose epsilon by 2 here. You can choose epsilon in 1 and 2 and obtain 2 epsilon later, then it will just be fine. So it doesn't matter. Just to make it look good, I chose epsilon by 2. Whenever, now let's write this as whenever x minus c less than delta, because we have replaced delta 1 and delta 2 by delta here. Okay, whenever x minus c is less than delta, that means whenever x is approaching c, our two limits L and L prime, the difference between them is less than epsilon, which means L is approaching L prime. Therefore, L equals to L prime. And our theorem is proved.